I'm remembering. All right, guys, on Tuesday, what did we discover? Who remembers? What about the ln of x? Jillian? Okay, yeah, we found the derivative of the ln of x. In fact, all logs, right? Logarithmic functions. I'm going to come around and check that homework. It was in the book. I hope you checked your answers. But today, we're going to discover the derivative of exponential functions. Isn't that exciting? Yes? Okay, so for the do now, what I want you to think about is what is the derivative of y equals the ln of x? And don't say it. I want you to, starting with y equals the ln of x, which is just log base e of x. In fact, I'm going to write that. That's my little hint here. I want you guys to find the inverse while I check homework. Just pause that. All right, so when we switch x and y, we get the inverse. So what do we get when we just switch x and y? Okay, yes, you're right. You're right. It is ln. So we're just going to write log base e of y. But now here's the tough part, because now you got to solve for y. And we're not. This is not multiplication. We can't divide. So this is, I know you know it. Anyone else think that? All right, Jack. Where's he getting that from? Ben. Oh, you remember that. Ah. Bacon and eggs. All right, whatever. All right, let me explain this, Ben. I don't know this, Ben, either. You can write equations in logarithmic form or exponential form, and you really want to be bilingual. Like when I write log base 10 of 100 equals, now let's think about what that would be. What's the exponent you raise 10 to get 100? 2, right? Whenever you have the log base of whatever number, it equals the exponent you put on that number to get this answer. Okay, this is logarithmic form. This is equivalent to saying what using exponents? 10 squared equals 100. We're saying the same thing, okay? This is logarithmic form. This is exponential form. Because you're more comfortable with base 10. That's why I went there. I know with the e. Does anyone know the number e, Euler's constant, what it equals around? Close. 2.7. Anyone know the next digit? 1. 2.71828. And then it goes on forever, just like pi does. What's that? No, I'm not like one of those pi kids that knows all the digits. Even whatever I knew at one time, I'm sure is gone. But yeah, you want to have an idea of what it is. Okay. Well, it's really, inverses are great. They help us simplify expressions in math. Remember the other day when we started to talk about inverses, we said that when you take the composition of a function and its inverse, and it doesn't matter the order, okay, if you start with x, you plug it into a function, you plug that answer into the inverse, what do you get back? What you started with, right? Because whatever a function does, the inverse undoes. And that's all an inverse function is. So if you have a point AB that's on the graph of f of x, what point has to be on the inverse? If AB is a point on the function, BA, remember all we're doing is switching all the x and y coordinates. So if you start with some number a and you plug it into the function f, what do you know you're going to get? And if you take that answer and plug it into the inverse, you're going to get back to a. Whatever a function does, its inverse undoes. It doesn't matter, right? You see it like that? If you start with b and you plug it into the inverse, what do you get? A, because the point BA is a point on the inverse. And if you take a and plug it into the function, you're back to b. Now, we just said that the inverse of the ln of x is e to the x. That means we're going to be able to simplify expressions where we have one of them plugged into the other. I know, because I'm trying to make a list already. So e to the x and ln of x are inverse functions, right? So if you take ln, if you start with x, you plug it into the ln function and plug that into e to the x, guess what you get? Well, if you start with e to the ln of x, though, you're taking x, you're plugging it into the ln of x. You're taking that and plugging it into the inverse, e to the x. What do you get? All right, we're taking x, we're plugging it into the function. Let's say the function is the ln of x, okay? So we're going to get the ln of x here, right? Because we're taking x, we're plugging into the ln of x. And we're going to take that value and we're going to plug it into the inverse, which is e to the x. There you go. And it doesn't matter the order. If we start by taking x and we plug it into the exponential e to the x, and we take that and plug it into the ln of x, what are we going to get back? Back to x. This is going to help you simplify expressions. Whenever you have one of these functions plugged into the other, you got to get them together, okay? You can simplify the expression. And it doesn't have to just be x. It can be anything. That's why I'm trying to make it like e to the ln of happy face. If you have e to the ln of happy face, what are you going to get? There you go. It doesn't matter. Don't get all hung up on the particulars. Or if you have the ln of e to the happy face, happy face. No, the nose was a bad idea. I wasn't going to do it. All right. Yeah, just keep it without. No nose. I know. You're saying that I got the concavity wrong. And, okay. All right. So if I ask you to differentiate this, I know you don't even know how to do that yet, but the first thing you should be thinking about is, how can I just simplify it first? Raise your hand if you think you know how to simplify this. No, wait, I got Ryan back there. The first one, yeah. Take a look at this. Anyone else think? You know how? Just raise your hand if you think you know you can how to simplify it. A few. What's your happy face, kids, in this case? All right, so what does it equal? This is just the same as saying sine x. Next time someone asks you how old you are, how old are you? Say I'm e to the ln of 17 or whatever you are. 17, it just sounds better, right? What about the ln of e to the 4x? 4x, right? You're taking 4x, you're plugging into the exponential function. Whatever the exponential function does, the ln undoes. So it gets you back to 4x. You all right with that? What's e to the ln of 7? What's the ln of e to the pi? Yes. You can't have a constant in here. You can have a, yes. 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 Okay. I needed you to see that because I'm going to show you what the derivative of e to the x is, and I want to make sure you guys can follow the steps. That's all I'm asking you to do. We're starting with e to the x, right? And what we want to do is we want to find, oops, it's starting, kids. My board is a little off. It always gets bad in that corner. It's happening. We want to find dy dx. That's our goal. So we're starting with y equals e to the x. And the first thing I'm doing is I'm just taking the ln of both sides. Now, as long as this side equals this side, the ln of this side equals the ln of that side. Is that okay? All right. What am I doing going on to the next step? This side stayed the same. What happened over here? Ln of e to the x is just x. We're just simplifying, right? We're okay with that? Very good. So now if the ln of y equals x, then the derivative of the ln of y has to equal the derivative of x. Okay? Now the question is, how do you take the derivative of the ln of y? We just did that on Tuesday. We used u instead of y, though. All right, if it was the ln of u, it would be u prime over u. What if it's the ln of y? y prime over y, or 1 over y times y prime. That's the same thing. You see this right here? This is the same thing as saying y prime over y. Why is it? I didn't know if you were just repeating it. Yeah, because y prime over y is the same thing as 1 over y times y prime over 1. Right? You can always break up a fraction like that. So we're saying the derivative of this side equals the derivative of that side. The derivative of this side is y prime over y, or 1 over y times dy dx. The derivative of x, that's just 1. Now, you want dy dx. We have 1 over y here, so what do we do to both sides? Divide by 1 over y, or multiply by y. So now we have dy dx equals y. What? What does y equal? E to the x. What? The derivative of e to the x is e to the x. Have any of you ever heard of that Disney song? There's a song, I think it's like an old Southern song or something. I am my own, my own grandpa. That's something you should like listen to in your own time. So, but that's what I was thinking of. This function is its own derivative. That's amazing. So, yeah, that's what we have to look at. That's what I want to look at. No, if a function is its own derivative, it's e to the x. Yeah, we have some other things we can do later, but they turn out to be equivalent. What function is its own derivative? Yeah, that's it. Yeah. But I really think that something like this takes a few minutes to digest. And so what I want to do, I have a graph of y equals e to the x here. And what I'd like you guys, oh no, it's going to do it, I can tell kids. I'm going to try, but. We'll see. Maybe it'll fix it for a few minutes. All right, let's try this again. All right. For the x values of -1, 0, 1, and 2, we're going to figure out the y coordinates and the slope. Okay? Now remember, y equals e to the x. In fact, let's just do that first. Like when x is -1, I want to know what the y coordinate is right here. I'm not even going to write it. Okay, so what is the y coordinate if y equals e to the x? 1 over e. It's e to the -1, right? Is that right? Okay, does that seem like it bothered you? All right, that worked. How about the y coordinate of this point here when x is 0? E to the 0 is 1. Good. Yeah, anytime you want any graph, you want the y coordinate, you plug in the x coordinate into the function, right? When x is 1, what is the y coordinate? E. And we said that's about what? 2.7. It's a little less than 3, right? Pi's a little more than 3. And how about when x is 2? E squared, right? Oh. All right, write down e squared on your papers. Let's try again. Now it just does like these little, it's not e to the 4th, that's an e squared. Yeah. Okay, now, do you think e squared is less than 9 or greater than 9? Why? Less than 3. All right, just checking. All right, now I want to figure out the derivative at each of these points. Now we know each of these points on this graph. I want to know what the derivative is. That is the slope, the derivative. Okay, so when the x coordinate is -1, the y coordinate is 1 over e. How do we get the derivative? It's the same thing. So the slope is the same as the y coordinate. But I'm actually happy that it's happening when Mr. Richmond's here because I have a witness. So it's actually a good thing. Yeah. That's recorded. But it doesn't do this when the tech guys come. That's the problem. Yeah. We said when x was 0, y is 1 right here. What's the slope right there? Oh my gosh. Well, we're going to draw these tangent lines in. Let's draw them in. But I want to just fill these out, and then we'll do it. All right? Well, you have to remember, these graphs are not, we don't use the same scale on the y-axis as we do on the x-axis. It's not exactly squared, so that's why. So when x is 1, y is e, what's the slope? And when x is 2, y is e squared, and the slope is? That was pretty good. All right, let's draw some tangent lines in. Let's actually see this. When x is -1, it's hard to draw tangent lines. When x is -1, we said the y-coordinate is 1 over e, and so is the slope. Do you think that's less than a half, more than a half, 1 over e? More than a half. More than a half, right? Wait, more than a half? Less than a half. The denominator is greater, so the fraction is smaller, right? Okay. I'm listening to the crowd. All right, you know what? I got to guess where it is. On your paper, draw a tangent line. Just see, I know I'm trying. I'm trying to draw a tangent line here with a slope of 1 over e. Well, it's going to get worse as we go over. But okay, so it's a little less. It's going to be less than a half here. Now we get to 0. What did we say the slope was? 1, same as the y-coordinate, right? That's a good idea. It actually might. I'm going to try that for the next one. When x is 1, what was the y-coordinate and the slope? E. So yeah, so I'm going up here. Well, I know your papers are going to look better. Ooh, that's good. No, that's not. All right. I had a part of. Oh, that wasn't good. No. Well, you're not seeing it? Well, what we're saying is you've got the greater the y is, the greater the slope. The slope and the y-coordinate are always the same. So when you have small y-coordinates, you have a small slope. As the y-coordinate gets greater, because the slope is the same as the y-coordinate, the slope gets greater. So as you go along, look what's happening to these slopes. It's just going to get steeper and steeper. Well, it's never going to get exactly vertical. It's just approach infinity. Okay, it's just going to keep growing. I'll draw my last one here. So at 2, the y-coordinate and the slope are both e squared. All right, the slope would be e squared there. So that's a pretty amazing function, right? It's its own derivative. Think that's going to be a hard one to remember? Derivative of e to the x? All right, do you remember it? What's the derivative of e to the x? Oh, that's good. Do you think I'm going to be happy sticking with just e to the x? No. No? No. Well, we're going to, if it was the ln of e to the something, we could simplify it. But we're going to want to differentiate e to the x squared, e to the sine x, e to the u. Who's going to come singing? Who sings that song, guys? Aretha Franklin. It's time for the chain rule. Well, this is it. You're not ready for this? You can handle it. If the derivative of e to the x is e to the x, what's the derivative of e to the u? E to the u, right? But, remember when you use the chain rule, yeah, you just take the derivative of the outer function, but then if what you plug in is not just x, it's some function of x u, what do you have to multiply by? What are you saying?
We know what to do.
Well, no, I need you to say it, though. If you are taking the derivative of a composition of functions, inside function is some function u. You take the derivative of the outer function.
Over here.
What do you multiply by?
The inside.
The inside function?
The inside.
Just the inside? Like, wait. All right. I'm going to give you a function that you're more comfortable with, okay? One that you already know. If I asked you to find the derivative of the sine of x squared plus 3, all right, what would the derivative? This is the function y. So you would just ignore the fact this wasn't an x. You would say it's just cosine of x squared plus 3. Multiply by what? The derivative of the inside function. Yeah, we got to be able to say it, right? You got it? Okay. So now we're taking the derivative of this now, the u is going to be your x squared plus 3. It's going to be some other function. So the derivative is going to be e to the u, but what do you got to multiply by? Okay, that's what I'm looking for. Du dx, what else can we call it? U prime. What do you guys prefer I call it? Oh, no, they're split. Okay, either one is fine. So it's e to the u times u prime. Well, when you apply the chain rule to find the derivative of a composition of functions, you take the derivative of the outer function, you leave the inside of function alone, evaluate it at the inside function, then you multiply by the derivative. Well, the derivative of e to the u is just like e to the x is e to the x, it's e to the u. That's the derivative of the outer function. But times the derivative of the inside function, u prime, which is you can call it u prime or you can call it du dx. Either way, it has to be the derivative of whatever you're plugging in there. Let's change this function slightly, okay? Let's make this function an exponential function. Let's say y equals e to the x squared plus 3. So e to the x squared plus 3 times, because it wasn't just e to the x, then the derivative would just be e to the x. It's e to the x squared plus 3 times 2x. No. Why doesn't it? Ah, but wait a minute. Are you, well, but you're plugging the u into the e function. You're not plugging, this is not e squared plus 3, right? When I say the inside function, you're taking this and you're plugging it into the exponential e to the x. But the inside, okay, so let me write it with f's and g's and stuff like that. All right, let's say that f of x equals e to the x, and g of x equals x squared plus 3. Okay? Let's say I want to evaluate f of g of x. So g of x is my inside function, and I'm plugging it into my outside function. Yeah. Does everybody see what this would be? What is f of g of x? Let me just raise this up. I'm sorry. So g of x gets plugged into f. So it's e to the x squared plus 3. So yeah, g of x, this is your inside function. All right, so when you take the derivative of all this, okay, you take the derivative of the outer function, leave the inside alone. So the derivative of e to the u, I'm just going to write y prime, is e to the x squared plus 3. And then we got to multiply by the derivative of the inside function, which is 2x. Well, because, well, you're saying if one of the functions was x squared, let's say if f of x equals x squared, and g of x equals, let's say, sine of x, f of g of x is equal to, yeah, and then when you go to use the chain rule to differentiate it, yeah, you do the power rule first because that's the outer function. And then you multiply by the derivative of the inside function. Okay? I think you're just bothered because the inside function's up there as an exponent, and it looks different. You're not seeing the parentheses. I get that. I get that. That what? Oh, Sydney. Okay. All right. That's for you. All right. So now we got to remember, if it's just the derivative of e to the x, it's just e to the x. But if it's the derivative of e to anything else, you copy. It's just the same thing. It's e to the u times the derivative of the exponent, u prime. Sure. What's the derivative of e to the first, kids? Nope. 0. Derivative of the exponent, 0. You got you. I didn't do it. All right, we're going to do the first one. We're going to do the first one together. Look at it. We want the derivative. That is a good one. Derivative of e to the 2x. Derivative of e to the 2x. Manny. E to the 2x times 2? Oh, yeah. Yep. That's what it is. So it's e to the u, so e to the 2x times the derivative of the exponent. Now, if I thought it would be legible, I'd write 2e to the 2x. It would look better, right? It's the same. If I thought it would be legible, I'd write it down. All right, I want you guys, we're using this rule to differentiate e to the u. I want you guys to try the next two, but you have to check with at least one other person. What's the maximum? 3. All right, from 1 to 3 people, but I want you to check. Do you take the derivative of both of these? Check with a couple others. Okay? Make sure you got it. All right, guys, I need a volunteer. The derivative of e to the sine x. Gina. All right, Gina says the derivative is e to the sine x times what? I'm sorry. Cosine x. Does anyone agree with her? Okay, that's good. Now, the next one, this will be interesting to see what you do. You might have it simplified right away. Tim, you want to try this one? Oh, you're showing me the answer. Okay. Everyone else get one? Okay. Well, tell me how you did it. Because there are different ways you could do this. E to the ln of x is 1. You're saying you're doing two things in one step. What does e to the ln of x equal? I like that you're simplifying it. Wait. E to the ln of x equals x. Okay. Now take the derivative. It is what you said, but you were doing two things at once. Yep. Mm-hmm. Yeah.
Wait, I got that, but I don't understand it. Like,
All
I
right.
get how to do it, but not up to that. Like,
Did you do it this way?
yeah, I did.
Okay. E to the ln of x can be simplified. Okay. What is x times 1 over x? 1. Yeah.
Wait, so e to the ln of x
Exact.
is equal to x.
Yeah. The derivative is 1.
But if I like e to the ln of like 2x, that would be
If it was e to the ln of 2x, it would just equal 2x, and what would the derivative be?
2.
2.
Oh, that's what you just said. Okay, got it. This guy's a tricky guy.
He's tricky. No, that's easy. He's easy. Get it? Guys, skip over these next two for a second. It's time for a silent challenge. Silent challenge. It's up here. Find the answer. Do not say a word. I thought you liked these. Yeah, it doesn't sound silent. Don't need a unit circle for this. Do we all have an answer in our head? And when I count to 3, I want you to hold up the number of fingers. Wait, let me just see what the answer is. Okay, ready? 1, 2, 3. Hold them up. You're not holding up fingers? You don't know? Wait a minute. All right.
Guys, even I know. Come on.
Just knows. All right. It is 5. Okay, a couple of people weren't quite sure. Look, what? Yeah. 3 sine x, that's just 3 cosine x.
So that's not.
You don't need to use a product rule when the first factor is a constant, right? It's first, no, you know this, because look, when you have a function,
Oh, you're right.
it's a product, no, yeah, you don't, okay,
Oh, then it would be 0.
yes, all right, so that was 5. It's just e to the u, you copy, times the derivative of the exponent. That was, all right. Now, guys, there are a bunch of exponentials out there that are not e to the x. They have different bases. Remember, y equals 10 to the x, y equals 4 to the x. Those other exponential functions, there are a ton of them. You don't want to be stuck being able to differentiate only e to the x. Now, I'm not going to go through this whole derivation. It works the same way that we found the derivative of e to the x. But if you want to take the derivative of 3 to the x or 4 to the x, the formula is almost the same, right? I'm going to give it to you here. It's still copy. The derivative of 4 to the x is still going to be 4 to the x. But you're going to have to multiply by the ln of 4, or whatever that base is. So it's the exponential a to the x times the ln of whatever the base is. Let me just see if we could get that one. So if y was, so if y equals 3 to the x, what would y prime equal? Well, the derivative of 3 to the x would be 3 to the x times ln of 3. Okay? Hey, why didn't we need that from when we had e to the x?
E to the ln e to the x.
ln of e is 1. The derivative of e to the x is e to the x times the ln of e. We just don't need that. All right, so I got to just throw this last piece at you. If you want the derivative not just of some constant to the x, but some function of x, u, let's apply the chain rule. Come on, we can do this. The derivative of a to the x is a to the x times ln of a. What's the derivative of a to the u? Well, the ln of a, but then what do we need? Times u prime. Same thing. It's just that, we don't need this piece in here with e when the base is e because the ln of e is 1. So this is the only formula you remember from today. It'll get you through every single case. This one right here. Yeah. No? Oh, man, I don't know if we're going to make it, kids. All right, let's just get through one. All right, let's just do one of them, though. Whoops. Sorry. What's the derivative of 2 to the sine x? Wait. Don't forget the middle piece, the ln of the base. Okay? Ah, good. Can you just one more? I know I'm being greedy. So what is the first part? Times Good. Those are good. All right, now go to the summary. We don't get another silent challenge, sorry. All right, let's go back. What's the derivative of ln of u? What if it was the derivative of log base b of u? That's what we did Tuesday. U prime over the ln of the base times u. Oh, kids, I'm sorry. All right, I'm going to leave that. All right, so the derivative of e to the u is e to the u times u prime. What about a to the u? Times u prime. Whoa. All right, guys, the homework that I have, because I know some of you are doing that replacement exam, I won't check it till Monday, because I know some of you are going to do that, and I am here after school today. Here? That's just because it's nothing. There's no reason. Yeah. No.